welcome back to our machine design series. Today we are talking about an introduction to fasteners. We are introducing you to the fascinating world of fasteners. And to get us started, I like to ask this question in class, and it is, how many screws and bolts do you think are in the average car? Your options are 100, 500, 1500, or over 3,000. So take a second, think about what your answer might be. And if you said over 3,000, you are correct. Now, if a car has over 3,000 fasteners, how many do you think are in a large jet, like the Boeing 747? And if you said over 1 million, you're correct, about 2.5 million. And each of those fasteners can be specialized to cost more than several $100s a piece. So fasteners, while you may initially picture the humble fastener that holds your light switch cover on, they truly are an extremely important mechanical component. They give us strength in joining components together. They're versatile. They are reusable, and so learning methods of joining parts together is an extremely important concept in the field of mechanical engineering and the design of machines. So today I'm just going to talk through some introductory topics to make sure that we're on the same page as far as terminology goes, knowing the different parts of fasteners, terms for different styles of joints, and then in the next few videos we'll start getting into more of the nitty-gritty, learning how to write a torque spec, learning how to come up with the joint constant, and then of course doing static and fatigue failure analysis of fasteners. So let's get started. Let's start by talking about the different types of joints that we might encounter based on the type of loading that is on that joint. So bolted joints can handle tensile loads, shear loads, or both. So I'm going to draw a tension joint and a shear joint. All right, now before I label them, if anybody wants to pause and venture a guess as to which one of these is a tension joint versus which one of these is a shear joint, feel free to do so. And then, of course, I'll show you that this one here is a tension joint on the left, and on the right we have a shear joint. So in a tension joint, the members are being pulled apart, loads are parallel to the fastener, and in a shear joint the loads are perpendicular to the fastener's axis, and they're trying to slip those joint members past each other. And you can have a combination of these two types of loadings in any given application, but these are the two strict classifications: tension versus shear. Next, let's talk about the different styles of fasteners. You may have heard these terms used interchangeably, but there is a technical difference between a bolt and a screw and a stud. So let me draw up what each of these looks like, and then you can take your guess as to which is which. All right, so here's our three types of fasteners. Classifications are bolt versus screw versus stud. So if you want to venture a guess as to which you think is which, go ahead and do that. All right, you got your answer? Let me tell you, this is the stud. So a stud is just a headless fastener. All right, it's a straight shank, it's got a threaded portion, and then in this drawing, I didn't draw the threads on the top, but there should be. It could be threaded all the way down, but in any case, it does not have a head on either end. Now a bolt is this first one here, and a bolt is a fastener that has a head, it has a straight, uniformly threaded shank that's intended to be used with a nut to clamp the whole assembly together. So this top portion, this is the head of the bolt, and then down here we have a nut. This one also has a washer. Okay, it may be fully threaded, or maybe only a portion of it is threaded like is shown here. And then finally we have a screw, which is this one on the end. It is the same as a bolt, except that it is intended to be threaded into a tapped hole instead of using a nut to secure the other end. Okay, so those are the types of threaded fasteners we might have. Now let's talk through a little bit more of the anatomy of a threaded fastener. Okay, so here's a rough sketch of what a threaded fastener might look like. This is, of course, a bolt. And as we said before, this top section here, this is the head of the bolt. And then this smooth portion here, which your bolt may or may not have, this is called the shank. Then we have, in this portion, each of these individual helixes is a thread. And we have a nut for this bolt that will be used to clamp two parts together, presumably. It could be more than two. So now let's talk about the threads themselves and basically zoom in a little bit here to one threaded section of a bolt. Or actually, I'm going to zoom in on the top side here just to make my drawing a little bit easier to do. Okay, so first let's define pitch, which is the distance between adjacent threads. So this is center to center. Distance between adjacent threads is known as the pitch. The major diameter of a bolt is going to be the diameter to this outer section of a thread, to the outermost portion of a thread. The minor diameter is the smallest diameter of a fastener, so just up to the root of a thread. And the diameter that we'll use for most calculations is the pitch diameter. And the pitch diameter is a theoretical diameter that lies between the major and the minor diameter. Not necessarily exactly halfway, but it does lie between the two. When a fastener fails in pure tension, it typically will break through the threaded portion or just underneath the head of the bolt. Because if we take a look at this bolt as we've drawn it here, where are our stress concentrators? We have one underneath the head of the bolt, right? We have this sharp turn, and I've drawn it with fillet radius, which is typical, but if you're designing a fastener from scratch and you forget to put in that fillet radius, you'll have a really high stress concentrator here. And then we have another stress concentrator basically at every single thread in the threaded portion of this bolt, right? We have lots of sharp corners. And particularly, you would expect to see failure most often at the first fully formed thread. That's going to be the biggest change from a smooth shank to the threaded portion, or in the first fully engaged thread in the nut, because again, that's going to be a change in both the effective geometry where we have this join between the nut and the threaded portion of the fastener, and also this is going to be where our load is applied. We want to be able to calculate the tensile stress area, which is the effective area in the threaded portion of the bolt that we can use to calculate the stress in the bolt, given a particular force that is felt through the bolt. So to calculate the tensile stress area, we can use this equation where AT is the tensile stress area. This is our major diameter. So if I come back up to our drawing, that's the diameter from the outermost portion of one thread to the outermost portion of the thread on the other side of the bolt, minus this decimal divided by P, which again is the pitch. So that's the distance between adjacent threads. And then, all that in brackets squared. This is a way that you can calculate the tensile stress area if you ever need to, especially if you have a non-standard bolt. For standard sizes, you can find tensile stress areas in your textbook in tables 8-1 and 8-2, and that's for both the UNS standard bolts and for the metric fasteners. Now let's talk through naming convention for bolts, and I think that'll wrap it up for this introductory video. So we have two different naming conventions depending on if you're working in US units, US customary, or SI units. In US customary units, we use the Unified National System. Okay, and a typical bolt spec you might see may look something like this. Do the 1/2 inch, 12, UNC, 3A, and we'll add the LH. Okay, take a second, try to guess what you think this all means, and then when you're ready, when you have your answer, unpause the video, and let's work through it. So this first number, this 1/2 inch, this is the major diameter. So again, that's the diameter from the outermost portion of one thread on one side to the outermost portion of the thread on the other side. For the UNS naming system, if it is less than a 1/4 inch, if it's less than a 1/4 inch diameter, then you will number the diameters. Or so a number 12 bolt, for instance, has a major diameter of 0.216, 0 inches. A number 0 bolt has a 0.060 inch diameter. So you can look those values up in tables if you have a bolt that is under a 1/4 inch. This next number, the 12, this tells you how many threads there are on the bolt per inch. And sometimes we abbreviate this as TPI. So for this particular bolt, it has a major diameter of 1/2 inch, and there are 12 threads per inch of length on the bolt. UNC, this is the classification of thread. So UN, of course, means Unified National. UNC means Unified National Course. You may also see UNF or UNEF. F stands for fine, EF stands for extra fine. Next up, we have this 3A. And this tells us, it tells us two things. So let's actually break this down into both the 3 and the A. The 3 tells us the tolerance specification. This tells us the class of fit. So whether we have tight tolerance or whether we have a loose tolerance, where things are loosely fit together, or somewhere in between. The A tells us the type of thread, and by type of thread I mean A equals an external thread and B is for an internal thread. So this is an externally threaded bolt, meaning simply that the threads are on the exterior of the bolt. A nut would have internal threads. And finally, we have this LH, and if you haven't guessed it, this tells us the hand of thread. So yes, there are both left-handed and right-handed bolts. This one is left-handed. And if we had an RH, that would be a right-handed bolt. So a right-handed thread is going to advance away from you when you turn it clockwise, and a left-handed thread will advance away from you when you turn it counterclockwise. So just remember, righty-tighty, lefty-loosey, but that only works if you have a right-handed thread. Okay, now for the metric bolts. Their naming convention is going to look fairly different from the UNS naming convention. So let's take a look at a typical bolt spec you might see. Let's look at an M12 by 1.75. And then we'll use 6G by 85. All right, so again, if you want, you can pause, try to guess what you think each of these things mean. Then when you're ready, unpause, and I'll start telling you. So the M, this simply means that it's a metric bolt. Nothing special there. The 12 tells us the diameter. And again, it's going to be the outer diameter of the bolt. The 1.75, this tells us something similar, analogous to threads per inch, but instead of giving it to us in threads per inch, they tell us the pitch. And remember that all of this is going to be in millimeters since we're in the metric system. So this particular bolt has a diameter of 12 millimeters and a pitch, so a distance between adjacent threads, of 1.75 millimeters. The 6G, again, this is a fit classification. So that tells us the tolerance. And finally, the 85 gives us the length of the bolt. And again in millimeters. So this bolt is 85 millimeters long. One more note before we wrap it up. This M, you could have a standard M, which is a normal thread, or you could have MJ, which has a greater root radius. And similarly, up here we have UN. So this UN means that we have a normal thread, but we could also have a UNR, which would be the greater root radius. And that greater root radius bolt in both the UNS and the metric system, it is going to help in fatigue applications, because if we have a greater root radius, we don't have as much of a stress concentrator in our thread. And also on this note while we're talking about different applications. So for the UNC, UNF, UNEF bolts, keep in mind that the UNC bolts, they are going to be good for general assembly, and if you have to do frequent disassembly, right? Because if I have a coarse thread, it's not going to take me as many turns of the bolt or of the nut to get a joint tightened. Whereas if I have a fine thread, then I'm going to have to rotate the bolt more times just to get that same axial movement of the bolt or the nut. So coarse threads are good when you need frequent disassembly, but they're not good for vibrations. They are just the standard bolt to specify, but if you have an application that's going to have high vibrations or need very fine adjustments of the torque or the preload, then a UNF or UNEF bolt might be better for those applications. And that's why they're used in automotive and aircraft applications, which is applications with lots of vibrations. Okay, so I think that is everything I wanted to cover in this video and an introduction to bolts. In the next video, we will talk a little bit more about how bolts are manufactured. We will talk about thread engagement, so some quick guidelines for how much thread engagement you may want to have. Talk a little bit about washers. So anyway, stay tuned for that. Thank you for watching, and hope to see you in the next one.